Today we talk about one important topics related to measure theory. Precisely we discuss convergence of sequence of functions in LP space. We first write out here LPX A mu norm P be a norm space. We also proved it. Okay. X a mu B X script A here. Okay. That means some algebra and some measurable set, some algebra and some measure. Okay. And then this one be measure space and E belong to the script A. Okay. Then what happened? Then Fn, we talk about Fn be a sequence of function, be a sequence of uh, value valued measurable functions. Measurable function on E. First one, we say that Fn converges to the function converges to a function if E to R closure, if limit n tending to infinity fn x equal to fx. Okay, fn x equal to fx for all x belongs to E. Okay, then fn converges to a function f. Okay, now we erase our portion and going to next definition. Next definition is that here number 2 fn converges pointwise. Fn converges pointwise almost everywhere to f if there exists a set, a subset of E with mu a equal to 0 such that limit n tending to infinity fn x equal to fx for all x belongs to E difference A. Okay, fn converges pointwise almost everywhere to F if there exists a set, a subset of E with mu a equal to 0 such that limit n tending to infinity fn x equal to fx. Okay, this one is converges to a function and this one converges pointwise. Then what happened? Okay, converges pointwise almost everywhere. Then what happened? Now we're going to this one. That means we write another definition of uniform convergence of some sequence of functions. Okay, in measure space. We write it here. Now we say fn uniformly converges in measure to a measurable function to a measurable function if e2 are closer, if limit n tending to infinity mu here x belongs to e such that fn x difference fx greater than equal to epsilon equal to 0 for all epsilon greater than 0. Okay, we say that fn uniformly converges in measure to a measurable function if e2 are closer, if this one equal to 0 for all epsilon greater than 0. Okay, now we erase that portion and going to some, that means proof of some theorem related to this convergence. Okay, x a mu b a finite measure space, be a finite measure space, and let E belongs to this A. Okay, and if be a sequence of measurable functions such that if A be a sequence of measurable function such that f n converges to f mu almost everywhere on E, then f n converges in measure to f. Okay, now we also discuss proof of this theorem. Okay, we write here proof. We have to show that limit n tending to infinity mu x belongs to E such that fn x difference fx greater than equal to epsilon. Okay, this one equal to 0 for epsilon greater than 0. Okay, we have to show that this one. Now we're going to be discussion of that let epsilon greater than 0 be given, and define an equal to x belongs to E such that fn x difference fx greater than equal to epsilon n belongs to this natural number. Okay, and bn equal to union of k equal to n to infinity ak. Okay, then what happened? Then we write here define an equal to this and bn equal to this one. Then we write here above. Note that here bn plus 1 equal to union of k equal to n plus 1 to infinity ak subset of union of k equal to n to infinity ak equal to bn. Hence bn is monotonically decreasing. Okay, hence bn is monotonically decreasing. Okay, now we discuss about some portion. Since if n converges to if mu almost everywhere on E, okay, then there exists a measure set A. Then there exists a measure set an in E with mu an equal to 0. Okay, and n0 belongs to natural number such that here fn x difference fx less than epsilon for all n greater than equal to n0, and x belongs to E difference A. Okay, E difference an. Okay. Then what happened? Then we mark it 1. Okay, now we write it now. Let x belongs to E, okay, such that 1 holds, then hence x does not belongs to an for all n greater than equal to n0. This implies x does not belongs to union of k equal to n0 to infinity ak, okay, equal to b n0, okay, equal to b n0. This implies that we erase our portion and going to further discussion of that, okay. So what we done here, we just write some big k monotonically decreasing sequence and fn tending to f mu almost everywhere equal to what we write it here, and x belongs to u e such that this one holds. Then what happened, x does not belongs to an implies that x does not belongs to bn0, okay. So now we're going to be another discussion, okay. This implies that x does not belongs to n equal to 1 to infinity vn. This implies x does not belongs to n equal to 1 to infinity vn. This implies that n equal to 1 to infinity vn subset of an, okay. This means that intersection of n equal to 1 to infinity bn is contained in an, okay. Now we erase that portion. Hence limit n tending to infinity mu of bn equal to mu of intersection n equal to 1 to infinity bn less than equal to mu of an equal to 0, okay. This implies that limit n tending to infinity mu of an equal to 0, sorry, mu of bn equal to 0, okay. Then what happened, then we write it here. Note that bn equal to union of k equals to n to infinity ak. This implies an subset of bn. This implies mu of an less than equal to mu of bn, okay. So what happened, so we erase our portion. অতএব therefore limit n tending to infinity mu an equal to 0, okay. So what happened, mu bn equal to 0, then mu an less than equal to mu bn, therefore limit n tending to infinity mu an equal to 0, okay. Now this implies that, so we write it here. So limit n tending to infinity mu of an equal to what, x belongs to e such that mod of fn x difference fx greater than equal to epsilon, okay. equal to 0. Therefore, what happened? Therefore, fn converges to f. Therefore, fn converges to f. Therefore, fn converges to f. Converges in measure to f. Okay. So we also discussed this proof where fn converges in measure to f. Okay. So we also discuss in measure theory this one. Now we that means we also discuss another some example related to these topics. Okay, we discuss today some example related to these topics. So we erase that portion now. So we write it here some example. Let here x equal to r and e equal to r, and fn x equal to 1 if x belongs to n plus infinity, and 0 if x does not belongs to n plus infinity. Okay, then what happened? Then obviously we write it here. Then what happened? Okay, then we write it f1x equal to what? 1 if x belongs to 1 to plus infinity, and 0 if x does not belongs to 1 plus infinity. Okay. Now then f2x equal to what? f2x equal to 2 if x here 1 x belongs to 2 plus infinity, and 0 if x does not belongs to 2 plus infinity. Okay, now what happened? Fn x equal to is here, so fn x converts to what? And obviously 2 infinity subset of 1 infinity. Okay, so what happened? In this way we write n infinity. Then what happens? Hence fn converts to f equal to 0 for all x belongs to r. Okay, because if you getting n, then after n times fn tending to f equal to 0. Okay, then obviously that means fn is pointwise convergent. Hence fn be pointwise convergent. Okay, now we erase that portion and going to further discussion of that. Now mu x belongs to x belongs to e such that f1 x difference fx less than greater than epsilon. Okay, equal to what? Equal to mu x belongs to e such that mod of f1 x difference 0 greater than epsilon. Okay, this implies what? Mu of what? f1 x, that means 1 infinity. Okay, then this implies what? This implies plus infinity. Okay, then and similarly this case such that mu of x belongs to e such that f2x difference fx greater than epsilon equal to plus infinity. Similarly this one done. Okay, because this one happened equal to mu 2 plus infinity, so plus infinity. Okay, and similar way we also write it now. What we write? We write it by similarly, hence limit n tending to infinity mu of those x belongs to e such that mod of fn x difference fx greater than epsilon equal to plus epsilon. Okay, so we write it in first, we erase that portion and going to the conclusion part. Okay, conclusion part is that fn be pointwise but does not convergent. That means fn does not converge to f equal to 0 uniformly. Okay, in measure. So next we also discuss another example related to this convergence. Okay, another example we write it now. Here let x equal to r and e equal to 0 closed 0 closed 0 infinity, and define fn x equal to x by n for all n belongs to natural number and x belongs to 0 plus infinity. Okay, then what happened? Then first one, a let x belongs to 0 plus infinity, then fn x equal to x by n converts to 0 as n tending to infinity, then fn converts to f equal to 0 on e. Okay, and now we discuss so fn pointwise converges to f on e. Okay, so we erase our portion and going to further discussion of that. Okay, so what we write it b portion, let epsilon greater than 0, then here mu x belongs to e such that mod of f1 x difference fx greater than equal to epsilon. Okay, equal to what? Equal to mu x belongs to E such that mod of f1x greater than equal to epsilon. This equal to mu, here x belongs to E such that f1x greater than equal to epsilon. Here equal to mu x belongs to E such that x greater than equal to epsilon. Now mu of such that x belongs to E, okay, f2x difference fx greater than equal to epsilon, okay, equal to mu of x belongs to E such that x by a difference 0 greater than equal to epsilon, equal to what? Sorry, here x by 2. Then this one equal to what? Mu of x belongs to E such that x x greater than 2 epsilon, okay, this one equal to mu of 2 epsilon plus infinity, okay, equal to plus infinity. And now mu of here x belongs to E such that fn x difference fx greater than equal to epsilon, equal to mu of x belongs to E, here x by n difference 0 greater than equal to epsilon, okay. Then this one equal to what? This one equal to mu x belongs to E such that x greater than equal to n epsilon, equal to what? Mu n epsilon plus infinity, equal to what? Equal to plus infinity, okay, for all n belongs to this natural number. Then fn does not converge to f equal to 0 in measure, okay. Fn does not converge to f equal to 0 in measure. So we discuss two examples related to this measure, okay. Some f is converges uniformly, some and f is does not converges uniformly, okay. When f is converges uniformly and when f is does not converges uniformly, we write it in short. Okay, here fn x converges to pointwise fx on E, implies and implies by mod of fnx difference fx converges to 0 as n tending to infinity for all x belongs to n. Okay, this implies and implies by fnx difference fx converges to 0. Okay, this one supremum of n belongs to this natural number. Okay, x belongs to e as n tending to infinity. Okay, here for all x belongs to e, this one pointwise and this one pointwise and this one be uniformly. Okay, then what happened? Then we write it now. That means fn, when fn is uniformly convergent and when fn is pointwise convergent, we write it here. Okay, and again we that means we write it and some, so we write it some here, that means proposition. Okay, then we stop this one, some proposition related to this convergence. Then we also discuss mean convergence, convergence in LP and LPV Banach space. This one we discuss later, but today as here write this some that means proposition x script a mu be measure space. Okay, be measure space and e belongs to this a, and fn be a sequence in L, be a sequence in this LE, and A belongs to LE. Okay, if fn converges to f in measure, then there exists a subsequence fnk of fn such that fnk converges to f mu almost everywhere on E. Okay, let x a mu be a measure space. Okay, and E, then fn be a sequence and fn converges, then their subsequence obviously converges to f. So today I stop here. If you get this type of video, please subscribe my channel and please give like, and if you have any questions, please write it in comment box. So today I stop here.